So we will be studying machine learning, and we will data classification using the iris dataset. So iris dataset was put together by Edgar Anderson and brought into statistics and by Sir Ronald Fisher. So it has 150 records, 3 types of iris flowers, 50 records for each, and for every iris flower, there are 4 measurements: the petal width and length, and the sepal length and width. So you did get my Jupyter notebook, right? You followed me with your notebooks, correct?
Yes.
Yes. Well, thank you. Okay, so this data set is included into Seabourn, so we can import it from the Seabourn, and from Seabourn it comes as a data frame, and we can print head of the data frame. So here are records, and there are 150 of those. Here are features of these records, so sepal length, sepal width, petal length, width, and classification of which record as a species name, Setosa, and then later on there would be other versicolor and Virginica, right? So in machine learning terminology, the records are called observations, samples, examples, instances. Just don't be surprised. All kinds of names are being used. And the features, the attributes are called features or attributes or predictors or independent variables, regressors, anything you want. So again, that is the nature of this world. Statisticians used to give their own names to pretty much everything they can. So we will be using Skylearn to classify this data. And in Skylearn, Skylearn requires that the data should be divided into separate objects. So we will be predicting the name of the species. So the species will be the target. This column would be the target, and that should be a separate object. And the other object will be the features by or independent variables based on which we will be predicting and trying to classify the observation. So we will import this time, again, same data set, but now we will import it from the Skylearn. And in Skylearn, the iris data set comes as a bunch. And bunch is something specifically prepared and formatted for Skylearn analysis. So we can type iris, and okay, so to distinguish the two irises, I named the one that we got from the data frame is iris with a capital I, and so this is iris data frame, and the iris that we have imported from Seabourn, I called it iris with a lowercase first letter, so call it a bunch. So we always, again, this is like a very good habit in Python, always check the data type, because it's very much depends on the data type, how the operators will be applied. So as you may see, the bunch contains numbers only. Sorry, not the bunch. In bunch, we can have iris data. So one of the components of the bunch would be iris data, and we print it, and it has only numeric data. And so this is first is sepal length, width, petal length, width. So just numbers, nothing else. That is the requirement of Skylearn. We can check the data type of the iris data. So bunches consists of numpy arrays. So it would be ND multidimensional array. NumPy array which contains only data. We can verify the shape of it because it's important to have our target and our independent variables to be of compliant shapes, and indeed it has 150 records, numeric records, 4 columns. So this is 1, 2, 3, 4. So in the bunch, we can, there is another object with the feature names. We can print it out. Those would be sepal lengths, widths, lengths, petal lengths, widths. So we know it is not as convenient as data frame, but this is how Skylearn works. So we can print feature names. We can see what are the feature names. So now iris target is the last column, or would be the last column of the data frame, only here it is encoded. It is encoded numerically, and again, this is how Skylearn works. So it has 150 rows, it is 1 by 50. So the zeros would be for, and we can print target names, and that would be zeros for Setosa, versical would be 1s, and Virginica will be 2s. So Skylearn gave us data that's already prepared for classification analysis. What we do next, we name it this iris data. So this object that was within the bunch, we call it X capital. So this is the convention that people follow. Big X is a matrix that contains the features by which we will be classifying the data, and Y will be the target. So iris target is Y, X is data, the sepal and petal measurements. So this has 150 records and 4 columns. This has 150 records and single column. So the first algorithm we will use will be K nearest neighbors, usually abbreviated as KNN. And so we will be doing classification with this algorithm. So the way all this algorithm work is, so you just imagine the, and so there is an example of clustering, right? And the kind of a bit of segue. So what we're doing right now, classification of data, is supervised learning. So we teach the algorithm to classify the data, and we know the results. We have this target. Target results already known. Clustering is an unsupervised learning. In clustering, you do not know the results, but algorithm is finding the centers for the data clusters and establishes that. So I'm just using this just to show how this is sort of working. So basically, everything is converted to a 2D graph, and here are the distances from one to another, and all of these distances can be measured, and the algorithm meticulously goes through all of the data and finds these centers. So that would be clustering. In classification, it is sort of similar, but a little bit different. So when we teach the algorithm, we already know the results. We know that those would be stars, those would be triangles. We also calculate the distances, so that would be an observation or sample or record in question, and we measure the distance from the unknown, from the this unknown sample to the known sample, to the nearest sample. So that is the origin of the name, nearest neighbors. So we can measure to one sample, that would be one nearest neighbor. We can measure to multiple, and we can specify how many nearest neighbors we will use. And once we measure these distances, we let those neighbors to vote. And they vote, and there is like various algorithms how the voting happening. It can be simple majority, and then there may be something to resolve conflicts and so on and so forth. And also the distance can be measured in different ways. And it could be Euclidean distance, which is a straight line. It can be a Manhattan distance, which is like you move in a New York, you go by street, and then you make a right turn, you take an avenue. So this is like different way. And there are other ways of measuring distances, and Minkowski is a combination of the Manhattan and Euclidean. So let's see. So it became a default. So at this point, we're at the very beginning, so we will be using defaults. So are you following me so far?
Yeah.
Yeah, okay. Any questions? Okay, I guess not. So I'm using Seabourn, and Seabourn I'm taking the data frame iris, and this is the Seabourn pair plot output. And so this is so the samples, the observations are colored by the species name, and here we can see that probably so on this petal length, and that would be sepal width, the data of versicolor and virginica pretty much intermixed. Would be hard to separate them. However, virginica is pretty well separated, pretty well clustered, right? So we can go through these graphs. Actually, this is sort of histogram, so a density, frequency density graphs, and we can see, for example, sepal widths. The variables very hard to distinguish, right? The mean is close. Mean would be this number right over here, and the variance is very close. And in particular for versicolor and greenest virginica, they almost indistinguishable, right? So, and we can see it from the scatter plot too. So probably if I would be, or we would be limited to kind of choosing which features we would use to classify the data, I would say we probably should be looking at maybe petal lengths and petal lengths and widths, because here the variables, this is where the frequency density functions help us very much. So we see that the variables are clearly distinct. The median, sorry, the mean is different. The good separation of variances. So I will probably use those. But luckily, we can treat a computer as a slave and just throw everything at the computer and see how well the algorithm will perform.
Excuse me, Mark. Can you make your screen a little bigger? Is that possible?
Yeah, I think it is. Oh, do you have the Python notebook yourself, right?
I have it, but I don't have it up. I've just been looking at yours.
Okay.
Oh yeah, that's better. Thank you.
Okay. So let's maybe go to it a little bit more. So this is pair plot. Pair plot is a combination of scatter plots of different variables. We have 4 of them, so we have 4x4 scatter plots. On the diagonal, there are like distribution functions, right? And we can see which variables are kind of different and can be used as a good differentiator and which are not so good. But, and again, over here, you may see that sepal widths and petal lengths probably would give a good differentiator, right? Petal lengths and petal widths pretty well. Samples are differentiated, but As I said, let's first of all see what the algorithm is capable of. And so let's get, so we looked at the data, we did exploratory analysis. Now let's do like brutal force. Throw everything at the algorithm and see how it will pan out. So the first thing we do is we import the class, instantiate it. So the terminology of the Skylern is, so instantiate the estimator. The estimator is the model. That's exactly what we instantiated here. Instantiate means we created an instance of it. And now over here, we gave it a name, and we specified nearest neighbors equal 1. So it means that initially we will be looking for one nearest neighbor. So we will make algorithm to determine the nearest distance, the other sample with the nearest distance on this scatter plot, and that would be the nearest distance. And based on what this observation was called, Sitoso versicolor, we will give this name to this data point in question, right? So that's what we will do at the beginning. So other parameters we are not specifying, so we'll set as default. A good practice always to print to see what the defaults are. And I'm not even going to explain you all of them. I just say that metric Minkowski means the distance, the method how we compute the distance. And in this particular case, it would be, trust me, that Minkowski will do pretty much Euclidean distance. So the nearest neighbors we will measure 1, and the other ones I do not want to murky your minds. There are weights, so it's quite a bit of things happening in the background. And now we train the algorithm. If you remember that we created two objects, X and Y, and X is the data that we use for classification. This is numeric data, sepal lengths and widths. And Y is the target, how we called, how this records or observations or samples, sorry, not samples, yeah, let's not use the word samples, were classified, right? So, but they are also encoded numerically, right? Zeros, 0, 1, 2. So we execute this command, fit, so knn, fit. So knn is our object. The command is function is fit. And we got a result, and the result is inside the computer. There is a model that went over all these combinations, sepal lengths, petal widths, all of these combinations, all of them. And they edited up with some weights, and it now exists in the computer memory. And what we can do now, we can create a couple of samples just out of our mind and see how the computer would classify those. And here they are, two samples, one with petal, I believe first is sepal, I'm forgetting, it doesn't matter what is first, what is, so there are two samples, and we execute the command knn predict, and here is the result. And now what does this mean? That 2 means that the first sample was classified as whatever was called 2, I believe it is versicolor, and 1 means okay, so I actually wrote this. So 2 is Virginica and 1 is versicolor. So that was the classification of these two samples. And we have no idea whether it is good or bad because the samples came out of nowhere. They're out of sample data, but that's what we may have in life, right? We have model, we trained the model. Now we found some kind of flower. We do not know which species it is. We measured its sepal length, petal length, put it into the model, and the model gave us the verdict. The first one was Virginica, and the second one was versicolor. However, to trust our algorithm, we need to do a little bit better work, and we need to know how trustful is our algorithm. And here is one way you can do it. So first of all, we can create another model. This time, we will use 5 nearest neighbors. So we specify the parameter, the number of nearest neighbors to be 5. So in this case, we will be measuring distances to 5 nearest records, data points, and an algorithm will be making decisions based on these 5 data points. And we okay, so this was new. This is the samples that we tried. So we trained this algorithm on the same data that before, only we specified 5 nearest neighbors. And now we ask it to predict what are the species of these 2 data samples that we have created, these 2, right, X new. And this time, the result is different. It's both ones, right? One stays for versicolor. So are you following me, gentlemen?
Yeah, I am.
Okay. Okay, so we have no idea which parameters are better for prediction, whether it is 1 nearest neighbor or 5 nearest neighbors.
Hey,
So,
Mark.
yes.
I got a question for you. On the models, why is the testing of the model first before you do the algorithm?
I'm not testing first. No, first I'm doing fit. I'm fitting the model.
Oh, you're fitting it. Okay, I'm sorry. Okay.
I'm training the model. Yes. Now
Okay,
we're
okay.
testing it. Predictive is one of the testing is okay. So at this point, what we did, we trained. If I said the word test, I misspoke. So we fit, which means we trained the algorithm, and then we made a couple predictions, right, with different versions of the algorithm. And now we need kind of evaluate it, how well it is. We need to know how good is our algorithm is. And now we're going into testing it.
Mark?
Yes.
I think I lost your screen. I don't see your screen.
Gentlemen, do you see my screen?
Yes. I still have it.
Yeah, I still have it.
Okay, Deidre.
I'll figure it out. Thanks.
Just a second. Let me find out who else joined. Okay, Deidre, I hope you're catching up. Okay. So now we go into test it, and to test it we need to have known data, and that is actually called why this method is called supervised learning, because we have data to test it. So we will use exactly same data set that we had, only this time we will test it. So we have 2 models, one with 1 nearest neighbor and the second one with 5. And so what we do is we run the result. This, I called it PN5, five nearest neighbors. I use the X test, the same data set that we used to train the algorithm, and I got some results. And I mean, if you would examine it by eye, you would see we know that first 50 would be one type, then it is another type of a flower, and all of a sudden here we see some ones and twos intermittent, right? And then we can print the target, and we can go into kind of this laborious comparison, this item by item, and we can do it if we have 150 rows. If we would have like several hundred or thousands, we no way we can do it. So we can, I would say, think of something better way of kind of comparing the results. So let's get the algorithm prediction with the one nearest neighbor. So here would be one nearest neighbor. So these results came as a NumPy array, and we should always kind of check data types and shapes. And what we can do now, we can create a data frame of the predictions. And so the data frame, I'll call it comp, to short of comparing. And it would be, I'm creating a, so what figures bracket means? Can somebody tell me? What is that I'm using to create data for data frame?
Could you repeat the question?
Yes. Okay. Okay, so this is a dictionary. I'm creating it from a dictionary. So this is the name, would be target. It will become column name, and the data would be iris target. And the next column would be predict, and the data would be PN1, and that would be predict N5. So this is how the data frame would look like. That is its shape. And now we can use our Python skills. We can create a loop, a for loop. And in a for loop, we can look at every, so I goes in a range of 150. So it goes through every single row of the data frame, which is 150 rows. It compares the location I target to make sure that the condition is if it is not equal to predict 5, then print the record, the entire record. And else if in the same row, same observation, we're looking for target that it is not equal to predict N1. So we're basically looking every single row one by one, and we're looking if this is not equal to this and not equal to this. And if it is either of those, then we print the result. And so here are the results. So we see that observation number 70 gave us one prediction, 72, 83, 106, 119. So those are the mistakes. So we can now use Python to compare the results, and we see that, let's say, N5 was sort of worse, right? So we may think that probably it would be better to use one nearest neighbor, but maybe it's not a good assumption. Let's leave it at this for the moment, because I would like also to show you another way to classify data. So just so we would remember what we did, just summarize it. So the K99 is working based on measuring the distances on a scatter plots, the distances from the data point in question to the nearest neighbor. So if we train the algorithm and we gave it a new data point, it will place it on a scatter plot, and actually not one but several of those, because we use multiple, measure the distances to the first nearest neighbor, the nearest neighbor, and classify it as this. And so on one round of the algorithm, it would be classification done by petal width, sepal length. Then it would do classification based on sepal width, petal widths, and then the algorithm would do voting, and then will give us the result. So that was K nearest neighbor classification.
So that data pretty much was telling you that N1 was the way to go, but we're going to keep going.
We're going to keep going because I mean, there may be issues, right?
Right. I got you.
All right. So we use another method, and it is called logistic regression. And logistic regression is sort of works like that. So this is like a funny chart. This is engineering flow chart. Does it move? Yes, no. Should it move? Yes, no. And if it should move, but it does not, you lubricate. And if it moves, but it should not, then you use duct tape. So this is like, sorry for this kind of funny explanation, but I think it gives you the gist of the logistic regression. So here is another, let me make it fit my screen a little bit better. So this is another representation, graphical representation of logistics regression. So here is a penguin, and something makes penguin happy, something does not, something does, and how the penguin will feel if like three things hit the penguin at once. So these three things may be: if he got squid, he is happy; if he got fish, he is happy; if he got hit by another penguin, he is sad; and if he eating crabs, he is sad. So this is like trying to determine the state of a penguin based on what happens in the penguin's life. So here is how logistics regression work. So here are multiple inputs, and it could be what penguin eats, or it could be this measurements of these flowers, right? These sepals, petals, and so on and so forth. Then there is linear model inside where these inputs X are combined. So there is like linear regressions happening inside. They are combined, and then there are logits. Those are units with some kind of numerical numbers, which is being converted into probabilities. And I mean, the reason I would like, so it's a different, it's not like distances, right? It's pure logistics, right? Pure based on what's in the data set, how the previous record was, or other records being classified, right? So there is like a pretty impressive formula, which you should say kind of resembles a little bit of normal distribution. So the good thing is you do not need to remember it. You do not need kind of to understand how this formula works and why it is in that kind of horrible, I mean, sorry, sophisticated, intimidating shape. And the reason I'm showing you is there is like something called neural networks. People are frequently talking about neural networks. So logistics regression is the simplest incarnation of the neural network. If you would have multiple logits, this hidden, at this point, there's one layer of this kind of a mysterious computations, right? And this is logistic regression. If you would have two or more layers, you would get pretty much a neural network. So those two are very similar, and by understanding how logistics regression work, you would pretty much have a perception of how the neural networks work. And this is like a good buzzword to know. And the other thing to remember is that once you got your logistics regression model properly trained, or if you would have a neural network, which also present in Skylearn, then you really do not know how it worked inside. You can't explain it. You only have the results, right? And you train, you test your model, you know you believed it in most of the cases, but you have no control over how it worked inside, because it's kind of an internal algorithm picks up these logits, and that's what I would like you to know about it, and just remember that logistics regression is close to neural network, and if you hear the word neural network, you shouldn't be intimidated. Okay, so let's use Skylearn to create a logistics regression model for the same data. And so again, we import it, we instantiate it. As usual, I suggest that you print it so you would see the defaults. And we already have our training data set and our target here. So we train the logistics regression model using the existing data, and then we ask it to predict, and we use the same, you remember, 2 samples that just I created out of my mind. By the way, again, something I want to show you that from time to time, Python gives you these pink slips saying that he's going to retire some feature. And again, the feature is that the solver. Your solver is being changed, so the solver is born. So we can sort of, again, I'm kind of telling you this so you wouldn't be intimidated, because it's a developing world, something is changing. So you get in this. So in the future, the default solver would be changed from born to LBFGS. And in order just to understand the big picture, we will leave it at this. And so here it is. Here are the results for prediction of these two new sort of flowers, two new observations that logistics regression came up with. And again, those are out of sample data. We do not know whether it is correct or not. We can compare it now to the KNN, but also we can run the logistics regression on the entire test data set. Sorry, on the training data set, and see what will come. And so this is our training and test data set, which is in our case is the same. So here is the result. What we can do, again, we use Python in order not to kind of do meticulous work of checking this ones and twos. We add this new result to the data frame. Now we have data frame with 4 columns. So target, prediction made with the KNN 1 nearest neighbor, 5 nearest neighbors, and logistics regression. And we update our loop code to check all. So we check and consistently going through every record, checking the target against column 1, column 2, and column 3, and print all anomalies out. So the loop is, if this true, then we print, right? So now we have results. So, and we see, so we can go over and analyze the results, and we see that logistic regression made mistake here. KNN with N5 and logistic regression also made mistake here. And here the logistic regression was on sample 72 was right, but KNN with N5 was wrong, and so on and so forth. So again, if you have a lots of data, no way you can go through that manually. And there is, I mean, obviously, we can write some code to compare and give us the metric. And one of the ways to do the metric just to see how many writes were out of the total number of sequences. But luckily, we do not have to do it because Skylearn already have this function written. So what we do, we import metrics and we print metric for logistic regression. So we compare the logistic regression to the target, and the result is 0.96. So if logistic regression will correctly classify the entire data set, we will get 1, right? So we do same for the other things that we tested, right? And we can print it out, and we can now compare and look at it. Are you following me? Is it?
Yeah, I'm following.
Yeah. Okay. Okay. So now we
Basically,
see.
that's saying the n equals 1 is 100% accurate then.
Yes, that's correct. So the KNN with one nearest neighbor gave us the best result. So let's analyze the results. And by the way, have in mind that we've been testing our algorithms on the data that we have trained it on. And if you do that, your KNN with one nearest neighbor gives the best results. And this is kind of a sort of a known problem. And here is a diagram. Okay, let me make my screen a little bit, just fit it all. Right, so imagine you have two samples. One is blue, the other is red, so one may be setosa, the other one versicolor, whatever. And you train the algorithm on one nearest neighbor. It will correctly classify everything because it knows the result, and the algorithm may be very complex, but it's internal. We do not care about that. So it would be like this green curve separating the two data sets, and you see how it kind of pulls out the sample that is like really outside, right? Outside of it. But that would be like green would be like K and N with one nearest neighbor. So that is what it can do if you train it on one nearest neighbor. So the problem with this data, it will perform well on the data set that you trained it on, but it is not generalized enough. And if you would have new data, you may not be sure that it will do the good job. So we would like to have something exactly as we talked about when we did the regression. We would like to kind of have our, either it would be a regression line or this separation line. We would like it to be smooth. We would like it to have as few inflection points as possible. And let's make, yes, so I hear a question, yes? No? Okay. So this is like this teaching moment to which I led you. And let's make sure that if I can prove it, right? So the way to deal with that is test the algorithm also on known data, but not on the data on which you trained it. And one of the ways of doing it is just to split your data set. And there is a function split in Skylearn, which we will use. And so use existing data set. And for example, we will assign 60% of the records would be in training data set and 40% to testing data set, and sort of makes sense because you would like to train it better. I mean, you always train hard in the gym so you can perform better in life. So test size, so there is a parameter. Test size would be 0.4. So and So here is the how the model would look like. So we imported it. Now we instantiate it. So I'm using comma to declare, right? To declare it. So train, test, split, right? So X is our data set with all 150 records. So Y is the target. Test size would be 0.4. So it would be 40% of 150 records. And random state is 4. So what is random state? It means that we can split it every time differently. So it would pick up different records to be testing records. So let's check what we got. So X train shape is 90 records. So it was 60% of 150. It's 90 records, 4 columns, sepal length, width, petal length, width. The training target is 90 records, 1 column. The test shape is 60 records, 40% of 150, right? 4 columns. And so the target is 60 by 1. And so now we repeat the same things that we did on the full data set, only right now it's a reduced, it's a training data set. And we use, first we do logistic regression. And again, we get on that kind of warning. We check the defaults and we have the results. And we compute the metric. And we compute the metric, so we trained the model on the training set of 90 records. And now we do prediction, and for prediction we take 60 test records, right? And we see the metric that is giving us a number, 93%. Do you follow me?
Yes.
Yes, thank you. Okay, so then we repeat it for K and N with the 5 nearest neighbors, and we get a result 96%. And then we do it for our best performer, which was 1 nearest neighbor, and it gave us 95%. So what we see over here is that on a new set of data, KNN with 5 nearest neighbors performed the best, because hopefully that give us more generalized model. So going back to that screen, so what KNN did for this particular sample, it looked at this distance, at this distance, at this distance, at this, maybe at this, and then took a vote of them. And it gave like this black curve, which performed better on the new data set. And that's exactly, I mean, the purpose of all these exercises is to create a model that would perform better on the unknown data. So the model that we can trust. So in this case, we have only 150 records. But what we can do, we can run this split one more time, and it would be split differently. Different 90 records would become training records, and different 60 records would become test records. And we can test it several times and see more results. What we can also do, and so we can see whether it is KNN with kind of a 1 nearest neighbor or 5 performs better, and how it performs versus the logistic regression. But I would say also an interesting question would be, what would be the best parameter for k nearest neighbors, whether it is 5, 4, 3, 10, 11, and so on and so forth. So first of all, do not throw away logistic regression, right? It may perform better on some other split on the data set. So it's kind of, if you have time, you do logistic regression and you do k nearest neighbors, and you never know which one perform better. Usually KNN is slightly better, but life happens. I mean, so now finding the best value of n, right? And the best value of n, again, we use the might of the Python. We create a loop, a for loop, and we change the n. And we change the n from 1 to 26. And I cannot explain you now why I put 26, just kind of decided to go that far. And so what is happening here? So we run this loop on the using k nearest model, and we change n. We change n from 1 to 26. And every time we do that, we run the prediction, we run the metric, and we record the metric, the results. And now we can plot it, and we can see how the accuracy changes with the change in the number of the nearest neighbors to which we kind of measure the distance. So with like 4, 5, we get in like pretty good results, 96%. Then it goes up to 98%, and then it drops. And it drops. It's exactly this issue of the the model is becoming too complex. It's another way. So one is underfit, the and like 20 over 11 over 20 is overfitting, so the results are bad. The results are bad, and so again, not that you should do it like doing such a wide range, especially if you have a large data set, and it may take computer some time, but it may kind of be reasonable to do it like, definitely you shouldn't be doing it at 1, right? I would say 1 should be taken out of the range immediately. You should go like from 3 to maybe 10, 11, and run this kind of a loop and see where your optimum is. Actually, I would say probably 15 is kind of a good number, right? To stop, maybe a little bit more. So this is how you assess your models. So you assess your models by first splitting your data set, and if you have a limited data set, or even if you have a big data set, you create multiple data sets out of it. So by using this random parameter in split function, right? You split, so we have 90 records for testing. So we pick up this 90 out of 115 different order. And so we trained algorithm on different data. We see how it works. Then we test. We use different records for testing, and maybe the one split that you kind of you would be, I would say probably do this finding the number of nearest neighbor first, just on the first split, and then go and create more splits to test to see how it performs. And maybe there would be an iterations that you need to do. But this is basically how you predict the future for the categorical variables, the classification, the how for labeling the data. So to summarize, in these last two sessions, we learned how to create predictions, how to make predictions for numerical variables, and that is the regressions. And today we learned how to do predictions for categorical variables. And this is logistics regression or the nearest neighbors. And those were both numeric regression and the logistic regression. This is all supervised learning because we had the data before. We had the data before, and we knew the answers. So, any questions? I'm pretty much done, and I do not want to throw. Yeah, please. I do not want to throw any more knowledge at you today because this is pretty intense. This classification is pretty intense. And what I would like you to do is to do a homework. And I suggest that you use the same data set, the iris data set, only this time. So we made prediction based on all four parameters, all four predictors, all four features. The four features, I mean, were the sepal lengths and widths and petal lengths and widths too. What I suggest is, and what I kind of also I think is reasonable approach is first you do this data exploration and you pick up the features that probably could give you better results. And once you picked up these features, you may do this prediction based on limited number of features. And that's what I suggest. So more is not always better. If you're picking up more features and those features are not well separated, like let's say over here, you see the versicolor and Virginica kind of data points are kind of intermixed, or actually here they are like sepal widths and sepal lengths. So adding this feature will probably add more to confusion rather than clear classification. So you pick up features something like that, right? Or like this, which is pretty actually exactly the same. So that's what I suggest you doing. So create a data frame out of this so actually that would be, you have to modify the bunch, and that's a good exercise too, right? So you just drop the columns you do not need, focus on the columns you have to. So out of 4 you would have only 2, and see how well the algorithm will perform. So any questions?
Hi, Mark.
Yes.
No questions, but I'm going to do the homework. But I also wanted to know, could I reach out to you? I'm going to try this on a different data set for a project I'm working. Would I be able to reach out to you?
Yes, please.
Okay.
I would say I do not know exactly which data set. So I have two statistics classes coming, right?
Okay.
And I have not yet decided which data set to use. And in statistics, I cannot use Python because not everyone is kind of Python developers, although kind of you may see. So we'll be doing something to somewhat similar in Excel, but Python is way more powerful and way more, um, I would say, in nowadays, I would say if you are deciding where to put your time learning whether Python or Excel, I mean, you have to learn Excel, you have to know Excel, but machine learning definitely you do with Python. In Excel, it is very limited. So I do not know what I will choose. I have some suggestions. John Tegan sent me a data set. I will look at it. It's a time series data. So you're invited to the statistics training.
Okay.
I cannot guarantee you that excitement as we had with Python. With Excel, it will be a little bit more tedious, more, I hate saying boring, but anyway, you're invited.
So will you send us invites for these statistics, or do we have to sign up with somebody else?
Emmy will.
All right, I'll get to Emmy for that then. Okay.
Yes, please sign. So we would have two classes, and definitely it would be more regression. So let's see what we will get. I'm interested to what I would like to do in statistics, kind of take a really big data set or much bigger data set and show the difference on how kind of the size affects us, and show the results on real data versus the specially prepared data. I mean, this data is great. This IRIS data set is great because we can see, we can learn what we're trying to extract, right? It's great for supervised learning. The real data may not may not give us such a clear answers, right? But it's kind of interesting to see how it will perform. So I do not know what I will choose. Maybe we'll do Iris again, only with Excel. So I have an interesting data set. I will look at it. So time series data is kind of interested in terms that data is already, I mean, there is a timeline, right? You have to follow the timeline. So it's interesting to work with the time data.
And we can get time data from some of our sources that go back years and years every 15 minutes and make pretty big data sets.
That would be interesting to look at. Actually, kind of a disclaimer. So my trade is I'm a signal processing guy, right? So I was working mostly, so signal data is time data. So that's my kind of bread and butter for many, many years. And I was working mostly with the inertial data that coming from acceleration sensors, from compasses, from gyroscopes, that type of stuff. But electricity, I mean, any time data kind of, maybe I will show you another trick too.
Right, electricity, gas meters, water.
Yes.
We can get it all.
Yes. Those are kind of scalars, so they're not like acceleration. They're three-dimensional, so there's a little bit more fun. But even those are kind of can give us something to see.
Great.
And we will do a little bit more statistics there. And if you miss statistics, then you would have kind of a good introduction to that. So, any questions or wishes? Okay, I see there was something.
Mark, hear me?
Yes.
For classification, is there anything else other than K nearest that you recommend?
I would say probably KNN to start with, but I mean, logistics regression should, I mean, if you have a bigger data set, maybe logistics will work faster.
Okay.
But I mean, logistics regression is kind of an older thing. KNN is newer. But I would honestly tell you, when you get an, I mean, on this data set, we got results like 90-something%, right? Usually machine learning, if you get a result like on real data, like 85%, that's probably as high as you can get, if it is real data. So you can, I mean, all this, let's say if you're moving in the world, like when you have mission critical application and you have to kind of sound an alarm or do something serious, looks like you're way beyond just this simple machine learning. You have to do way more than that. You have to do kind of a sophisticated feature extraction, create new features that would allow you to kind of to do better prediction. This kind of initial throwing the algorithm with kind of defaults and so on and so forth, 80%, 85% is pretty good.
Okay.
And I mean, KNN may give you 95%, the other one will give you 93%, and I believe in the real world practice that would be enough either way. So yes, Dieter, please give me your example. I mean, maybe ideally if I can also use it in training later, maybe next year, that would be great too. But anyway, I will help you as much as I can.
Thank you. I'll be in touch. Thank you, Mark. I really appreciate it.
Okay. Okay, anything else?
I'll just say I thought this has been terrific.
Thank you very much. Oh, yep. I will send you the survey form. Please kind of give me a feedback. I need your feedback as detailed as possible. And thank you all very much. And see you next time, or just contact me whenever you need.
Thank you, Mark.
Thank you.
you.
Take care.
Thanks. All right, bye-bye.
Bye.